Okay, so thanks. So I should say it's really an honor to be invited here as a computer scientist who basically fakes his way in physics. I mean, if you guys think that you're confused about amps, I mean, I would be thrilled to be half as confused. So okay. So you probably saw, many of you saw earlier this year there was a very striking paper by Daniel, who just spoke, though not about this, and by Patrick Hayden. I should say that regardless of sort of what you think about the argument and its relation to the physics questions and where the firewall debate eventually goes, sort of I regard what they did as sort of one of the more remarkable syntheses of physics and computer science that I've seen in my career. So of course, the point that they were making is that if you consider this, I guess by now familiar to all of you, a setup where here is an old black hole. It's radiated away at least half of its stuff. And here's the old Hawking radiation, R. Okay, here's like the fresh Hawking radiation, B. Then yes, in principle, there should be an experiment that an infalling observer, Alice, could do where she would detect that R and B are entangled with each other. In fact, maximally entangled. And yes, this seems like a problem because the quantum field theory also tells you that B should also be maximally entangled with the stuff inside, and that would violate the monogamy of entanglement. Okay. However, they give arguments that in order to see that R and B are entangled, the quantum computation that Alice would have to do would almost certainly require exponential time. Okay, meaning exponential, say, in the size of the black hole, the number of qubits involved. Okay, which means before Alice barely even dent, the black hole would have long ago evaporated anyway. Okay, so maybe there's nothing to worry about. Okay, now, I imagine that perhaps, some of you might want to debate about, the physical relevance of this result. Okay, so, so one perspective that you could take would be, well, look, the entire AMPS problem is to figure out, what is the structure of the Hilbert space. Right? What is, a structure that can accommodate both, the experiences of someone who's outside and also someone who goes in, and that upholds, the equivalence principle and, and whatever other principles we think should be upheld. Okay, and obviously, if, how much time Alice needs to measure a particular operator, is like an engineering detail, right? It has, nothing to do with sort of the, the real, the structure of the Hilbert space, which is the thing that really interests us. Right, that's one position you could take. Okay, another position would be, well, yes, it's true that the Harlow-Hayden argument, doesn't solve the problem by itself, right? And Harlow and Hayden say as much in their paper. Okay, but it might be used in conjunction with some other solution, right? As sort of one of the prongs that makes you feel less bad. Okay, because the whole point of AMPS is that at least one of the postulates that goes into the derivation of this paradox has to fail, right? But if that failure of one of our principles, like having a smooth horizon or whatever, can be pushed into unobservability, well then maybe we feel less bad about it. Okay. So all of these questions are outside of my professional expertise, which is convenient in a way. Okay, so I'm actually not certain that if they're within your professional expertise, but they're definitely outside of mine. So, so this is not to say that I don't care about the laws of physics. For example, if there were a violation of quantum mechanics that Alice could observe, outside the black hole, right, I would be extremely concerned about that. But whether semi-classical, field theory remains a good approximation in the vicinity of the horizon, whether it only breaks down at the singularity or whether it breaks down earlier than that. Right? I mean, these things, these are really your problems, not mine. Right? As far as I'm concerned, if Alice is going to burn up at the horizon, she can burn up. If she's going to fall through, she can fall through. Right? I would tell her to try it out and send me a postcard saying what happened, except that she can't. So I'm not even certain what we're talking about. Okay, but no, I mean, look, these are deep, and fascinating questions. But, in some sense, sort of my entire talk is going to take place sort of safely outside the event horizon. The question that will interest me is, well, is it really true that Alice needs an exponential amount of computation to decode this entanglement between R and B, between the early and late Hawking radiation? And, how can we know that, right? I mean, we don't have the detailed theory that describes what's going on at the event horizon. So, and of course, there's huge amounts that we don't know about computational complexity. So how certain could we possibly be of such a conclusion? And on what grounds? Okay, and then, I'll leave sort of the discussion of all these, what, if anything, any of this means about the interior and so forth. I'll leave that to you, and I'm happy if people want to talk about that afterward. Okay, so the first point that I can make is that, the arguments that Harlow and Hayden made, were really quite careful. Okay, they were really quite good. Okay, I mean, like, it would have been cool enough, for me, if they had simply used sort of the basic sort of undergraduate tools of computer science, right, like NP completeness, for example, and had, connected that to black holes somehow. Okay, well, in fact, they do in their paper make an argument, one thing that Alice could do, would be like decoding and error-correcting code, and there is an NP-complete problem involved there. Okay, and they do make that argument. However, then they correctly realize that, well, wait a minute. This argument only rules out one particular strategy that Alice could use, one particular kind of strategy that Alice could use to decode the Hawking radiation. Right? It doesn't apply to arbitrary strategies of Alice. Okay, and really, we'd like to say that, no matter what quantum computation Alice does, as long as she's sort of restricted to a reasonable amount of time, which we tend to call polynomial time, okay, that, she's not going to be able to do it. Okay, and they realize that in order to make that sort of a better argument, they need to reach for sort of more recent and more exotic tools from computational complexity. And in particular, they rely on a hardness assumption. It's about quantum statistical zero knowledge. I'll tell you about it later. Okay, the details are not important for now. But the main justification for the hardness assumption that they ultimately relied on came from my PhD thesis 10 years ago. So I was really happy about that. Okay. Okay, but this story sort of then takes a bittersweet turn, which is that on Sunday, on the flight here, I came up with a different hardness argument for the Harlow-Hayden decoding problem, and my new argument sort of only requires sort of a more conventional hardness assumption, arguably a safer one. Okay, but so it's, you could view it as an improvement, but you no longer need my PhD thesis. So what can I do? Okay, so here's my plan for the rest of the talk. So first I'll explain how Harlow and Hayden sort of modeled the problem, modeled Alice's task as a computational problem. Okay, and I'll just be following them for that part. Okay, then I want to tell you about why we think that the problem is hard. But first, I'm going to tell you, how do computer scientists ever argue that anything is hard? So I'll give you a little digression about that, as it's relevant to me. And then I'll show you my new hardness argument. And I'll explain what are still the open problems about it, because it turns out that even if you just forget entirely about black holes, just think about quantum computing, there are lots and lots of fascinating, really nice open questions that come out of what they do. Maybe some of it is relevant to black holes also. Okay. So how do we formulate the problem? Okay. So as I said. Alice is outside the black hole. We imagine that she has complete access to R. Okay, so she can scoop up all the Hawking radiation somehow. Now, following Harlow and Hayden, I'll assume for most of this talk that Alice does not have access to B until the very end. Okay, so Daniel tells me that the reason that they make that assumption has to do with gravitational back reaction. That if she goes in to get B, that she's going to alter the state of the black hole. Okay, I don't know. It's convenient to assume that she's only operating on R, but in fact, if you want Harlow and Hayden's original hardness argument, the one based on quantum statistical zero knowledge, that one goes through even if Alice can act on B also. Okay, my new one only works if Alice can only act on R. Okay. Yeah, that's right. That's right. That's right. So they're incomparable. Fine. They're two incomparable arguments. Good. So yes. Okay. So what are the okay? And as I said before, I don't care about A. Okay, if it exists, if it doesn't. Okay, and even H, which is the horizon modes, is sort of only going to be of interest to me as something that decoheres R and B. Okay, so Alice doesn't have direct access to it. Okay, and I'm also going to assume, just for simplicity, that B consists of just a single qubit. Okay, why? Well, because if B were larger, then I would just simply take a large part of it and just redefine it as part of R. Okay, so and that would only make Alice's task easier, and therefore my hardness argument stronger. Okay, so in other words, I only care about sort of decoding entanglement between a single qubit down here and whatever Hawking radiation is up here. Okay, now I'm further going to assume that the entire black hole, the entire setup, can be modeled as a finite collection of qubits. Okay, let's say there are n qubits in total. Okay, and n will sort of be the parameter that sets the scale for our complexity analysis. Okay, and then what can we say about the dynamics? Well, obviously, I don't know what's going on, if it's M theory, if it's ADS-CFT, but whatever is happening to sort of scramble these qubits, I'm going to assume that it can be modeled somehow as a quantum circuit. Okay, so what is a quantum circuit? So this is how we draw them in quantum computing theory. So you have a collection of qubits on the left, and then you get to apply a sequence of operations, each of which has to be local, which means each of which has to act on only 1 or 2 qubits at a time, and as the identity on all of the remaining ones. Okay, so we can draw them like that. And furthermore, I'm going to assume that this is an efficient quantum circuit. Okay, what does that mean? That means the size of the circuit, meaning just the number of gates, or the number of these little unitary operations that compose the circuit, has to be at most has to be bounded some polynomial function of n. Okay, so it's at most n to the O of 1. So yeah.
Can I ask a question which we discussed at dinner the other night?
Yeah, sure.
I'd really like to understand better.
Sure.
So just in solving problems as physicists, we're familiar with situations where you pick a certain kind of variables to begin with and work with those, and it's incredibly hard, but if you're clever, you might find, say, a dual set of variables in which the problem really simplifies. And so I'm having a hard time understanding how strong an assumption statements like you just made are.
Okay, so there's something really strong that I can say, actually, which is the following. Okay, you might ask, what is the justification for making any of these assumptions? I claim that there's actually a really, really strong one, which is the following. That if any of these assumptions were to fail, then Alice's decoding task would only become harder. Right, in a sense. So, so like I'm giving, I'm trying to give Alice a fighting chance here, if you like.
I guess I'm being slow.
Yeah.
I guess I'm being slow.
No.
How do you show that that's the case? I mean,
Okay. I mean, there is. Okay, so I should say first of all, that there are sort of beliefs, in quantum computing theory, there's this charge Turing thesis, right? And there are, there's the idea that sort of the laws of physics, whatever they are, should be modelable as some as some sort of quantum computation, right? As some quantum circuit. Okay, and there are, we know this in some special cases, right? Jordan, Lee, and Preskel had a paper about, how do you simulate a 5/4 quantum field theory with a quantum computer. But, what I'm saying is, even if that were to fail, if the laws of physics let you do something more powerful than this.
Sorry, I'm not. I'll just try one more time. That's my question, and then I'll shut up.
Yeah.
But
all right.
I have in mind not a situation where you couldn't do it like this, but that doing it like this is much harder. It requires more steps or something.
Right.
Than it would if you had chosen more clever variables or something.
Okay. So I think there is to translate it into sort of my terms, right? There is sort of a real issue here, and an important one, which is that for some of the arguments, I'll just assume that the circuit C is arbitrary, right? But of course it's not arbitrary, right? The laws of physics, whatever they are, determine some particular C. Okay, and you might what?
I think we still I think the answer to the question.
Yeah.
If there was a better set of variables, that would just be the first 2 gates of the quantum circuit.
Well, that's one. Yeah. Well, that's one way to put it. I mean, a quantum circuit is able to do quite a lot, right? It's able to what? Well, all right. Well, we're going to get into that. We're going. That's coming. That's coming.
Actually, could you just say something about the locality? Is that what is the relevance of that?
Okay. Well, so
replace a more complicated thing with these all the time.
Right. So okay. So the reason why we assume locality in quantum circuits is that the laws of physics are local, right? We can only engineer interactions between pairs of particles at a time, and moreover, if we drop that assumption, if we said you can just do some arbitrary operation on all n of the qubits, right? Then we haven't restricted anything at all, right? Then you can just do anything whatsoever, right? So yeah.
Can I try Eva's question once more?
Yeah, I'm going to get into what is the evidence that that things are hard, or what kind of evidence.
Let me try it once more.
Yeah.
We could try to simulate the scattering amplitude in quantum field theory by reducing it to qubits, and then decide it was very hard. We could also do it by Feynman diagrams and find out it was very easy.
Okay. So right. So
No. That's right.
Right. So Feynman diagrams in my picture would correspond to just a special quantum circuit that happens to be easy. Okay, it's certainly not true that any quantum circuit is going to give you a hard problem. So the claim that I'm, going to give sort of general arguments for, and that Harlow and Hayden do also, is that as long as this circuit is sufficiently mixing or sufficiently scrambling, then, generically, we expect, a hard problem. Or rather, the more exact statement is we expect a problem that if you could solve it, would let you solve many, many things in classical computation that it would be very surprising that you could do.
Just a different variant. Could we imagine that they're sort of analog computing devices? And what I have in mind by that is, if we want to measure the state of something, often in physics we build experimental apparatus or apparata that interfere things and so on and so forth. And do we know that those have similar limitations?
So that's a big question. I mean, you can view any system in nature as a computer that simulates itself, right? So, the entire, content of this, Church-Turing thesis, or, its modern variants, is that it shouldn't matter, right? Because, analog computers, right, you can only measure things to some finite precision, and as long as everything's approximated to some finite precision, then you can simulate it with a Turing machine or a circuit anyway. Okay, so that's sort of that's the thesis anyway, and I think that some support for it would come from the holographic principle that says that if you go ultimately to the quantum gravitational degrees of freedom, then you really do just have a finite number of qubits within a bounded region, and not an infinite number. But however, whatever you think of this, it's not really relevant to what I'm going to say, because again, if there were analog powers that let you do even more, then Alice's task would only be harder.
Well, again, you might imagine that there's some way of unscrambling the message is to build some kind of analog apparatus in advance, and then the black hole evaporates. You run the outgoing radiation through the apparatus, and
so that's true.
What state?
Okay. So my claim will be the following: that if Alice could build such an analog apparatus, then she could also build an analog apparatus to invert one-way functions, which would collapse one of the main pillars of modern cryptography and modern computer science. Okay, so that may not be a big deal to you, but it is a big deal. Okay. So that's what I'll be able to prove, right? And so it doesn't matter what kind of computing device Alice is using, right? If she could solve this problem by whatever means, then she could do these other very spectacular things. Okay. Good. So Okay, so to recap, we can define the, what I'll call the HH problem, the Harlow-Hayden problem. We could call it the Hawking radiation decoding, which has like an acronym HARD. I don't know. Let's just call it the HH problem. The problem is that Alice is given as input a description of a quantum circuit, acting on n qubits, which produces an output state, which is a pure state, a tripartite pure state, okay, psi RBH. And here B is just a single qubit. Okay, R and H can be many qubits, and we are promised, we're guaranteed that the reduced state, if we look at B and H only, is the maximally mixed state. I'll borrow Daniel's notation for that. Okay, so this is all scrambled, and we're also promised that there exists one qubit of distillable entanglement between R and B. Okay, and Alice's task is going to be to apply some unitary transformation, U sub R, to R, so that some particular, qubit of ours that she has control over, let's say the last qubit, forms a Bell pair with B. Okay, so that's Alice's task, and we're interested in, whether it's easy or hard. Okay. And so as I said, to build intuition, it's easiest sort of first to study the scenario where we get to choose the circuit C, where it can be anything we like as long as it's polynomial size. Okay, then we have to worry about we don't get to choose it, right? The black hole dynamics just are what they are. Okay, so then I'll give arguments that as long as C is sort of sufficiently scrambling, sufficiently complicated somehow, in fact, I would think that if anything, the problem might only become harder than the special case that I know how to give arguments about. Okay, that's not that's not rigorous. I don't have a theorem that applies directly to the case where C is like completely scrambling. Okay, but I certainly don't see how it would become easier in that case. Okay, so now I have to get to a question that I guess Eva and some others have touched on, which is so how do we argue that something is hard, right? It's not enough to say I tried to do it, I don't see anything better than brute force search, right? That's a type of argument that people gave for a long time, but often you give it and then there is a more clever way to do it, right? And this has happened again and again and again in computer science, that people find a change of variables. They find some clever rewriting of some clever cancellations that let you solve a problem in polynomial time that you thought required exponential time. Okay, so what is it that we can do? You may have heard of this P versus NP problem. It's one of the 7 Clay Millennium problems, I guess. And so P is just the class of all decision problems, so yes or no problems, right, which are solvable deterministically by an algorithm, running on a classical computer. That uses only a polynomial amount of time. Okay, so when computer scientists say a problem, we mean something involving an infinite collection of inputs. Okay, each input is just an instance of the general problem. Okay, so a good example would be I give you an integer x written in binary notation, and then is x prime or not? Okay, and we'd like to solve that problem in time, which is polynomial in the number of digits of x, in the size, in the length of its binary representation. Okay, now this turns out very, very non-obviously to be doable in polynomial time. Okay, that was discovered 13 years ago. Okay, 11 years ago. Although we knew for a while before that how to do it by probabilistic algorithms. Okay, but so this primality problem is in P. Okay, and this is already an example of how the obvious way would be just trying every divisor, and that would require exponential time, but there are much better ways to do it. Okay, so now NP stands for non-deterministic polynomial time. By the way, I think that if we had been physicists, we would have called this the firewall versus flame ball problem or something, and it would have it would have sounded a lot sexier. But we're stuck with these acronyms. Okay, but. So NP stands for non-deterministic polynomial time, and NP is the class of all decision problems where if the answer is yes, then there is a polynomial size proof or witness that lets you verify that you can verify in polynomial time and be convinced that the answer is yes. Okay, so a good example here is, let me just pick one similar to my last one. Just given an integer x written in binary, does x have 5 or more different divisors? Okay, now this is a problem that we don't know how to solve in P. Okay, it's closely related to the factoring problem. Okay, and in fact, some of you might know that the security of most of our electronic commerce, anytime you order something from Amazon, your credit card number is protected by the assumption that this sort of problem is not in P. Okay, so many people want factoring to be hard. Okay, yeah.
That's not quite right because they're all finite problems.
Yeah. Yes, that's true. Okay, so there's all. I knew that this was going to, someone was going to raise this at some point, right? There's always this caveat that you can say, okay, you're solving a fixed problem, right? Well, like, what is the complexity of chess, right? Of knowing who will win at chess. Well, the answer is it's L of 1, because chess is just a finite game. So simply enumerate all the possible positions, and then you're done. Okay, so that's not very enlightening, right? And so to get anywhere with in complexity theory, right? We have to sort of say, look, we're interested in asymptotics, right? What we really care about is how does the difficulty of our problem grow as the thing gets larger. And in fact, it's been proved that if you generalize chess suitably to an n-by-n board, then it is, depending on how long you allow the game to continue for, it's either p-space complete or x complete. In the latter case, there would actually be a proof unconditionally that it is not solvable in polynomial time. Okay, so which is kind of cool. That's fairly rare, by the way, as you'll see. Okay, so all right, so the P versus NP problem, so it's clear that P is contained in NP, right? If you can find the solution yourself, you can, you don't need to have this witness even, okay? But so the question is every NP problem also a P problem, okay? Or in other words, if you can program your computer to efficiently recognize a solution to a problem, then can you program your computer to efficiently find a solution? Okay, that's an equivalent formulation. I would, actually argue I might get vegetables thrown at me, but I consider this the greatest open problem in mathematics, greater than even the Riemann hypothesis and all the rest. And my argument for that is that if P were equal to NP, and if the algorithm were fast enough that you could implement it in practice, then you would not only solve this problem, but you could also solve all the others, because you would simply program your computer to say, find me a proof of the Riemann hypothesis with a billion symbols or fewer, in the language of Zermelo-Fraenkel set theory or whatever. And if such a proof exists, then it would spit it out, and then in not that much time. Okay, so but this is an open problem. So you might ask me, you might say, well Scott, if computer scientists can't even prove this sort of obvious seeming statement that there are some NP problems that are not in P, right? Then how then you don't really know anything, right? You're just your whole field is conjectures, right? How do you how can you say anything is hard? Okay, so the easiest response to that would be look, I've been going to talks here all week, and for you to accuse us of too much hand waving. Okay, but maybe a better response is just that there's like I've learned from working in quantum information that there's a difference in terminology between fields. Okay, what mathematicians or computer scientists call a conjecture, is typically what physicists would call a law. Okay, so they say, look, we have this principle. It survived every test that anyone has tried to throw at it, right? So in this case, P versus NP, right? People have been thinking about algorithms for or polynomial time algorithms for 60 years maybe, and there have been sort of I would say sort of thousands of cases where if an algorithm had just worked in a slightly different way then it would have given you P equals NP. Okay, and yet it never happens, right? In fact, when you try to solve these hardest problems in NP, you always seem to need exponential time. When, if so many things had been just a little bit different, then you would, be able to do them in, some sub-exponential time. Okay, and so after, so you can say, look, this is a principle that that has withstood a lot of tests. We don't have a proof of it yet, if you like, at a mathematical physics level of rigor, and and that's one of the great challenges of mathematics. Okay, but in the meantime, one can say that if P equals NP, then the world would be very different than we think it is. So in some sense, the question in computer science is not will you need some assumption to, in order to argue that your problem is hard, right? Because almost always you will, right? As I said, in a few cases, like chess for n by n board with unlimited amount of time, or the halting problem, we can actually prove that, that you can't solve it or you can't solve it efficiently. Okay, but in most cases we can't do that. We can only prove hardness under some assumption. Okay, but so the real question is just which assumption do you need? Okay, so if you have to assume, okay, my particular special problem is hard, then that's not very convincing. But if you can say, look, either my problem is hard or else P equals NP, if my problem is easy, then this whole universe of of tens of thousands of other problems comes crashing down. Then that's much better. Okay, and the big discovery in the 1970s that really started this field off is that for a huge number of problems of practical interest, you actually can do that. Okay, you actually can say these problems are hard unless P equals NP. Okay, so this was, if you've heard of NP completeness, right? This is what it's about. So very roughly speaking, a problem is called NP hard if it has this property that you can show that if you could solve it, then P would equal NP. Okay. And then the NP complete problems are the problems that are both NP hard and in NP. Okay, so those are like the hardest problems in NP. And and actually, there are now like I think tens of thousands of problems that are known to be NP complete. Okay, so let me So if you can show your problem is hard, only assuming P not equal to NP, and that's sort of like the gold standard of hardness. Okay, that's actually really good. Okay, now unfortunately, we can't, we don't know how to do that in all the cases of interest to us. Sometimes, we have to make a stronger hardness assumption. Okay, and so there's sort of a whole hierarchy of different hardness assumptions you can make, right? The stronger they are, the less certain we can be in them. Okay, so because it will be relevant for me, let me sort of just tell you some of what is in that hierarchy. Okay. All right. So let me just draw arrows. So going from the top will be weaker assumptions and therefore more secure, more likely to be true, more certain to be true. Okay, so at the very top, I'll put P is not equal to NP. And, and actually what will be relevant for us is the analogs of all of these hardness conjectures for quantum computers. Okay, so the quantum analog of this hypothesis is called NP not contained in BQP. Okay, BQP stands for bounded error quantum polynomial time. Basically, it's just basically it's just like the quantum computing version of P. It's the class of all the problems that are of all the decision problems that are efficiently solvable using a quantum computer. Okay, and we also, although many sort of popular articles may give the impression otherwise, we also strongly believe this. Okay, we do not have a fast quantum algorithm to solve NP-complete problems. People have looked for one for a long time, and most people would actually conjecture that it doesn't exist. That yes, quantum computers do sometimes give you exponential speedups over the best known classical algorithm, but only for sort of some very special problems like factoring integers. Okay, not for NP complete problems, we don't think. Yeah.
In particular, if I'm allowed to use exponential space, can I convert every problem to a simple problem?
Well, you can't. I mean, no matter what resource bound you give, I can give you harder problems than that, right? I can give you problems that would require triply exponential space or whatever. Okay, but yes, all of the problems that I'm talking about would be solvable if you had exponential space. But you don't have exponential space.
Okay, but this is, I mean, time is just a generalized resource. So all your resources are limited, and whatever direction you move, this is invariant with respect to.
Well, okay, so I should say something about that. So when we talk about, like, you can talk about, like, P space, which is the class of problems you can solve with a polynomial amount of memory. But in some sense, that's, like, way too large to correspond to a class of feasible problems, because a polynomial space algorithm could easily run for exponential time. Right, and so the time is not bounded, right? Whereas, on the converse is not true. Okay, if your time is bounded and if your computer is local, spatially local and so forth, and just does like one operation per time, then it's only ever going to use a polynomial number of memory cells, right? So your memory will be bounded too. Okay, so polynomial time you can think of as, it just corresponds to a polynomial sized circuit, okay, or a polynomial number of gates. Okay, yeah. Okay. So what? Okay. But as I said, we can't really get everything that we'd like from assumptions that are this generic. So what else is on the menu? Okay. Well. A slightly stronger thing that you could assume is that there are problems in NP that are hard on average. Okay, so P not equal to NP would only say that there is some problem in NP such that for every polynomial time algorithm that you could design, it will fail on some input to the problem. Okay, but those inputs on which it fails, those tricky inputs, might ironically themselves be extremely hard to find. Okay, so so NP hard on average would say that you not only does P not equal NP, but you actually have an efficient way to generate input instances on which any polynomial time algorithm will fail with a high probability. Okay, and and again, there's also there's quantum analogs of all of this. NP should be quantumly hard on average. Okay, and we also believe that. Okay, now going to a stronger assumption, you can conjecture that there exist what are called one-way functions, or ALFs. Okay, so what is a one-way function? Okay, well, intuitively, it's just a function which is easy to compute but hard to invert, meaning hard to find any preimages. Okay, so a one-way function is a function f that maps n input bits to some polynomial in n number of output bits. It's an infinite family of such functions, one for each n. Okay, but it has to satisfy two properties. F has to be computable in polynomial time. So f of x is computable in time, polynomial in n. And secondly, for every polynomial time algorithm A, which tries to invert f, it only succeeds with a small probability. So we can say the probability over all strings x that f of A of f of x equals x is less than 1 over polynomial in n. Okay, so what is this saying? It's saying that you have any polynomial time algorithm has only a negligibly small chance of finding any preimage of f of x. Okay, with where the probability is over x. Okay, so for in particular, just setting f of x to always be 0 doesn't count as a one-way function because you can easily find some preimage even if it's not the same x that was used to as the input. Okay, so So this is one-way functions. One-way functions are sort of the most fundamental building blocks of modern cryptography. Okay, once you assume that one-way functions exist, then it's known that you can get secure private key encryption systems, with a small key. Okay, you can build them out of this, and you can rigorously prove that if someone can, break your crypto system, at least within the mathematical assumptions. I don't mean with side channel attacks. Okay, then they must be able to break the underlying one-way function. Okay, you can also get out in the same way. You can get pseudo-random generators, right? Cryptographically strong pseudo-random numbers from one-way functions. You can get digital schemes for digital signatures. Okay, so all kinds of stuff. And furthermore, the belief in one-way functions is still quite generic. Okay, by that I mean that you don't seem to need any sort of special mathematical structure to get a one-way function. Okay, if you just take any transformation of your input, which is sort of sufficiently scrambling, right? Just like run some cellular automaton on your input, or just do something complicated to it, right? There's a very good chance that you'll end up with a one-way function, or so it seems. Okay, now by contrast, if you want public key encryption, like where you don't have to agree on the key in advance, for that you need what's called a trapdoor one-way function. Okay, and that's what requires sort of special mathematical assumptions, like that factoring is hard or something like that. But if you just want a bare one-way function, then that seems somehow very, almost as generic as just P not equaling NP. Okay, so now we can still go further down. We can make an assumption, which I'll call the finding collisions is hard assumption. Okay, so. So here's what this assumption says. It says that suppose that we're given, a function. So meaning, we have like an efficient algorithm to compute this function. And now this will be a function that maps n input bits to n minus 1 output bits. Okay, so just by counting, we know that this function must have many collision pairs, meaning there must exist many input pairs x not equal to y, such that f of x equals f of y. Right. And so now the task is just to find any such pair. Okay. So intuitively, right, if f were sort of completely generic, right, then you would still expect this to take exponential time, right? I mean, there's this birthday paradox, right, that if you put there's a very good chance that two people in this room have the same birthday, right? And based on that phenomenon, you'd only need to look at about 2 to the n over 2 values of f before you found a collision pair with high probability. Okay, so now the thing that I did in my PhD thesis, which I mentioned earlier, is that I proved that even if you have a quantum computer, which can make quantum queries to this f, so it can evaluate f in quantum superposition. Okay, again, if f is generic, then even a quantum computer is going to need at least 2 to the n over 3 accesses to f to find a collision. This turns out to be achievable, actually. This is tight. Okay, so a quantum computer gives you some speed up for this problem, but only an n to the 2/3 power speed up over what you get classically. Okay, so now to be clear, my result does not prove P not equal to NP or anything like that, right? Because it requires the assumption that f is generic. Okay, you know nothing about its structure. Okay, as soon as you're told, here is the algorithm to compute f, then it's entirely possible that either a classical or a quantum computer might be able to exploit that structure to do better. Okay, and so if you want to believe that it can't, then that's, then you have to make an assumption. Okay, but this is again a known assumption in cryptography. It's actually also used a lot in modern cryptography, that you can have what's called a hash function, where finding just a collision, finding two strings that hash to the same output is a hard problem. Okay. Yeah.
You assume that these ones exist in general, or that the ones you're considering?
Oh, so you just assume that there exists some hard function, right? Well, what you show is that you give me any such hard function, and then I can give you a crypto system, which will be secure, which will use that function and which will be secure, assuming that your function was hard. So if my crypto system, is insecure, then it was your fault. Okay, this is the kind of result that people prove.
There are all these things that are hard in some that we don't know, and then there are the algorithms we actually use that we don't know.
Well, yeah, but the point is that your ignorance of one can be linked to your ignorance of the other. Okay, that's what you can do, right? You can say that, instead of coming up with this complicated crypto system and just saying, well, I don't see how to break it, right? You can say, if someone can break my crypto system, then they can also break this sort of extremely generic assumption that people have, studied for like the last 40 years or whatever. Yeah, okay, good. So, all right, good. Okay, and then below that, we can have, sort of the least desirable thing to do, would be just to make various special assumptions, like, that this particular problem is hard, right? Like, we could assume that, factoring is hard. Well, that's actually what we have to do with, if we use our RSA for our encryption. Okay, but in this case, we actually know that if we have a quantum computer, then that assumption that factoring is hard is actually false because of Shor's factoring algorithm. Okay, there are other public key crypto systems that we don't know how to break, even with a quantum computer. But but for each one, you have to make some kind of special assumption. Okay, so to be clear, these special assumptions are considered by everyone to be good enough to base all of the world's electronic commerce on. Okay, but we're going to take for granted that they're not good enough for arguing about Alice's decoding of Hawking radiation. Okay, and we want to do better than that. Okay, so. Okay, so now I can summarize sort of what's, what can be done. So basically what Harlow and Hayden did is that they showed that, decoding the Hawking radiation is at least as hard as this finding collisions problem. Okay, they didn't state it that way. They stated it in terms of this class of problems called quantum statistical zero knowledge. Okay, but it's extremely closely related to this problem of finding collisions. Okay. The other thing I wanted to say is that finding collisions, they get some intuition for its hardness. So the famous problem of graph isomorphism, can be easily reduced to finding collisions. Okay, so graph isomorphism means that you have two graphs, G and H, and you want to know whether they're isomorphic. Right. So let's suppose that you just looked at two gigantic lists, one consisting of all n factorial permutations of the vertices of G, and the other consisting of all n factorial permutations of the vertices of H. Okay, and then you look for collisions in this list of two n factorial graphs. Okay, and now, let's assume for simplicity that G and H are rigid, so they have no, non-trivial automorphisms to themselves. Okay, then if you find a collision in this list, it must be between something up here and something down here, which then means that you have found, an isomorphism between G and H. Right, so a lot of interesting things can be reduced, can be expressed as this finding collisions problem. Okay, and what they showed is that, all of those things would be solvable, if you could solve this HH, this, Harlow-Hayden problem. Okay, so then what I can do is I can do a bit better. I can show that the Harlow-Hayden problem is at least as hard as inverting an arbitrary one-way function with a quantum computer. Except one little caveat: the one-way function has to be an injective function. Okay. So that's just a technical condition. That's also a known, thing in cryptography, that sometimes you need injective one-way functions. Okay, but that should, that's again a pretty generic belief, right? Because let's say if you have a function with n input bits and let's say more than 2n output bits, right? It's just enough output bits to evade the birthday paradox, right? Then probably if your function is sort of random, then with high probability, there won't be any collisions anyway, right? So this is a pretty reasonable belief that there's an injective one-way function that's hard to invert by a quantum computer. Now, it might not be obvious that this belief is sort of any better or more secure than that belief, but one thing that I can say is that it's known that sort of if you could invert arbitrary, one-way functions, then you could easily find collisions. Okay, whereas the converse is not known at all. Okay, whereas if you could invert injective one-way functions, then at least you could find collisions in sort of pairs of injective functions. Okay, so in some sense, this problem really is sort of strictly harder than that one. At least if you ignore the injective part. Okay, so. All right, so now, let me, with all of this setup, I can now sort of explain to you in about 5 minutes, why it is that if you could solve this Harlow-Hayden problem, then you could invert injective one-way functions. Okay. The construction is really a simple one. Okay. So what do we have to do? So we're given some function f, which we know how to compute in polynomial time, and we're told that it's injective, okay, and we're told that it's a one-way function. Now we need to show that we can create a state, of R, B, and H, okay, such that if someone could decode the entanglement between B and R, then they would also have inverted F. Okay, so how do we do that? All right, well, I can just write it down. So we're going to prepare the following state: psi of RBH be equal superposition over all n-bit strings x so x, this is just x padded out with zeros in the Hawking radiation, 0b plus f of x comma 1 r 1b x h. Okay, so this is going to be our state. Okay, so I claim that we certainly, if we know how to compute f, then we can certainly prepare this state efficiently. Okay, I just, put x in I apply a quantum circuit that puts x in superposition, and then, I put this b in superposition, and then conditioned on b being 1, I compute f, write it into this register. Okay, I can do all that with a quantum computer, no problem. Okay, and now you'll notice I'm even being very generous, and I'm just giving you which qubit of R should be entangled with B. Okay, it's this last one. Okay, these two are the ones that should be entangled. Okay, and the only problem is that right now they're only classically correlated. Right? You don't why? Because this x and f of x over here is decohering the entanglement. Okay, so all you got to do to make these two entangled is to reverse this decoherence over here. All right, so what can you do in order to do that? All right, well, as I said, in general, what Alice can do is that she can apply some arbitrary unitary transformation, call it U sub r, to the state of the Hawking radiation, okay, meaning to all of this stuff. Okay. Now, I claim that we can assume without loss of generality that U sub r maps basis states of the form x, comma 0 to output states of the form psi sub x 0, and that it maps basis states of the form f of x, comma 1 to outputs of the form phi sub x, comma 1, for some psi's and phi's. Okay, why? Well, because we know that if the thing succeeds, then at the end the last qubit has to be maximally entangled with B. Okay, and so it has to be in some bell pair with B, and so if it's in a different bell pair, then I can always just do some simple rotation to this last qubit to put it into this form. Okay, so all right, so what that means, let me back to this board. Yeah. Well, as I said before, for now, I'm just going to assume that I get to create psi RBH by a polynomial size circuit of my choice. However, I can then give you an argument later that if psi RBH were created by, let's say, a random circuit or something sufficiently scrambling, then the problem should only be harder than this special case that I'm considering. Yeah. Yeah. No, sure. I mean, it could be that once M theory is known, right, that it has some special property that makes the problem easy, right? Not knowing M theory, right? I can't tell you that. Okay, nothing I say can rule that out, right? All that I can tell you is that if the sort of dynamics are sufficiently scrambling or something, then you would generically expect the problem to be hard.
To make it so that you can do this.
Exactly. Thank you. Yes. Right. So I can, at a physics level of rigor, I can give you that, I think. But, yeah. So, right. So, and if I get to design the dynamics, then I can really make it, as hard as one-way function. Okay. So, all right. So let's just do this. So because of this, I can just say, look, let V be the unitary transformation just obtained by, that's induced from U by just fixing the last qubit to 0. Okay, so V is a unitary that maps each x to psi sub x. Okay, then certainly we know how to apply that, right? Just fix the last qubit to 0. Okay, then let W be the unitary transformation obtained from U sub r by fixing the last qubit to 1. Then W, which we then also know how to apply, maps f of x to phi sub x. Okay, but now we're essentially done because if we look at like W dagger V applied to x, then that will just be W dagger psi x, which is f of x. Okay, and conversely, if we look at V dagger W applied to f of x, then that will be V dagger applied to psi x. Oh, I'm sorry. There's one missing step in that I forgot. Okay, the missing step is that Okay, so we I'm sorry. We have to ask what has to be true about psi x and phi x in order that the entanglement will be decoded, in order that these last qubits will be encoded. And I claim that actually it is, for them to be maximally entangled, it is necessary and sufficient that psi x equals phi x. What? Huh? Good. Okay. That was, I got sidetracked. I'm sorry. Okay. So, yeah. So, Good. And that's why I'm allowed to make this substitution. Okay, and now you can give an approximate version of this whole argument. Okay, and this is what would be necessary in order to in order to recohere the entanglement, right? And furthermore, you can say that even if you just want the last two qubits to be approximately in a Bell pair, this has to be approximately true. Okay, or approximately true for most x's, and that's then enough to make the argument go through. Okay, so it's robust in that sense. Okay, so now using this equality between psi x and phi x, we then get this, that by applying dagger w to f of x, we can get x. Okay, so so v and w are like bridges that Einstein-Rosen bridges that go between x and f of x. Okay, so an extremely interesting point about one-way functions and quantum computing is that the normal a quantum algorithm to evaluate a function would actually do this. It would take x comma 0 and map it to x comma f of x. Right? This, if you know how to compute f, then you can always do this. Okay, but we don't expect that we can always do this kind of mapping, even if f is an injective function. Okay, because if f were a one-way function, and if you had a quantum algorithm to do this mapping, then you could simply reverse it in order to break the one-way function. Okay, and that's exactly what what you're able to do here. Okay, so as I said, Harlow and Hayden had a different hardness argument, and in their argument, the construction is sort of interestingly different. You would put the f of x into h, into the horizon modes, and then the input x would be in the radiation, and that gives you a reduction with different properties, and with their reduction you no longer need the injectivity constraint, which is a plus. But I don't know how to show that you could break a one-way function. Only that you could do this sort of collision finding task. Okay, so that's so one open problem would be can you actually base this base all this on the assumption that p is not equal to np? I can't rule that out, right? Or that np is hard on average. Can you go up in this hierarchy of yeah? Yeah. Yep. Yeah. So in fact, Harlow and Hayden give such a counting argument in their paper. It's the first argument that they give in their paper. However, they then correctly point out that a counting argument doesn't really get you to where you want, because we know anyway that the states that come out are not generic. We know that they're produced by some physical process that presumably has some can be simulated by a quantum computer in some reasonable amount of time, and the number of such processes is not different such processes is not nearly enough to allow a counting argument to go through. Exactly. That's the whole point of a one-way function. Not just that it's hard to invert, but that it's easy to compute going forward. That you know how to.
The black hole produces the state
following. Yeah. Yeah, right. That's right. Okay, and to answer the question from before, if in the general case, we would expect that instead of being classical states, over here and over here, that these would both be some arbitrary complicated quantum states. Okay, and you would have to do a mapping that would get this one, bizarre complicated quantum state to this other quantum state, right? Your V and W would have to go between these two quantum states, neither of which you know how to even produce efficiently, let alone map between them. So I think that would only be harder than this. I mean, this is a special case of that, right? But I don't have an argument that for like a random circuit that it's hard or something. Okay, so that's another open problem. Now a third, one of my favorite problems, in this that's raised by this work, and one that I've been thinking about a lot this week, is the question. Okay, so I've shown sort of what computational powers would be necessary to solve the Harlow-Hayden problem, right? That you'd have to do, be able to find collisions. You'd have to be able to invert one-way functions. Okay, but one can also ask the converse question. What computational powers could you give to Alice that would suffice to enable her to solve the problem. Right, assume that suppose that we've modeled it correctly, right? Then how powerful would Alice have to be in order that she could do it? Right? And very, very interestingly, I don't have a good answer to that, right? I don't know, even if you gave Alice the power to solve NP-complete problems, or the power to do p-space, that this would be enough. Okay, because the problem is, Alice might be like this, super intelligent, goddess, right? She might, know exactly the description of the unitary that has to be applied. Okay, but still, she has to apply the actual unitary to this actual physical state. And if that requires an exponential number of operations, then it doesn't matter how smart she is, right? If there's just no efficient way to do it, to be found, then it doesn't matter that she could find such a way if it existed, right? So
isn't that the only problem?
Well, no, it's not the only problem, because even if there were an efficient way, even if there were a polynomial-sized circuit that decoded the entanglement, there would still be the task of how do you find that circuit. Right?
No, she has all the time in the past.
Oh, okay, sure, okay, fine. Okay, okay, fine. So, all right, so if you allow, Alice exponential time to get herself ready before the black hole forms, then then you're right. Then but then, I don't know how to show that, like, if P equals P space, then there must be polynomial-sized quantum circuits or any result of that kind. I would love to have such a result. Okay, and I think maybe it's even true, but I don't know. So those are all questions that I like. Oh yeah, I mentioned that the Harlow-Hayden reduction also works if Alice can act on B as well as R, but mine doesn't work as far as I know in that case. So I'd like to fix that up. And then you can ask, does any of this have any relevance to sort of asking about the black hole interior, right? And so in conversation, Lenny suggested to me that maybe the interior is sort of some computationally scrambled version of the degrees of freedom in the exterior, right? Or maybe that sort of the mapping between the two is computationally intractable, right? So do these sort of arguments give you any sort of leverage into establishing that sort of conclusion? I really have no idea, because I don't even know what the mapping should be before arguing whether it's hard or easy. But I'll leave you with that. So thanks. Yeah.
You've argued elsewhere that it would be a problem if the laws of physics allowed you to convert computationally hard into easy problems. And Joe and Don and their collaborators have argued that you could in fact do that for Alice's problem by computing in some asymptotic region where you can do it faster thanks to blue shifts and red shifts. And would that be in that class of situations that you would object to?
Well, yes. So I tend to be very skeptical of any proposal saying that you can get in the real physical world that you can get an exponential speed up just by sort of various time dilation tricks, right? Because and part of the reason is that I know many examples where that people have talked about where it doesn't work. Okay, for example, there's instead of the quantum computer, there's the relativity computer, right? Where you just set your computer working on a hard problem, then you travel at relativistic speed, you get back to Earth, exponential time has elapsed, all your friends are long dead, but you really wanted to know the answer to this question, now you have it. If if your computer was actually still running now, right? And so but interestingly, if you think about this enough, you find that this really doesn't work. And the reason why it doesn't is that in order to get an exponential speed up, you would have to accelerate so close to the speed of light that you would need an exponential amount of energy. And so then, instead of doing it, like the fuel tank of your spaceship would collapse to a black hole or something, long before you could do this. Okay, so likewise, where if you could get really close to an event horizon but not quite into it, and then back out, again you need an exponential amount of energy. So I'll put as a thesis or as a conjecture that that the laws of physics have like a censorship of exponential computational speedups. Right? This is something where again I've seen in many examples whether it's really true. Of course we can't know until we know the final theory of quantum gravity. And so that's an open problem that I leave for you.
Why can't I just lower myself down on a string and wind up some...
Well, you can, but you'll need an exponential amount of energy. So then again,
you'll... far away, yeah.
But okay, you can, at least in the various cases where I tried to calculate it, right, you always seem to need an exponential amount of some resource, right? So it's like if you just look at one resource and ignore all the others, then it can look like you're getting an exponential speed up.
It could be like what I said before, that the resource might be something you could use before you even do the experiment.
So okay, in fact, I think that Jonathan Oppenheim in his talk this afternoon is going to discuss a situation where if you could create the black hole yourself and in such a way that it were entangled with the Hawking radiation and you got to control it, then you could maybe solve the problem. But one thing that's relevant is I should say that for the argument that I gave, the argument based on one-way functions, okay, we still believe that one-way functions should be hard to invert, even with a quantum computer, even if you have arbitrary what's called advice. Okay, so like I can give you any string like to tell you a secret about this one-way function, right? It should still be hard to invert, right? There's no trapdoor. So even if you've spent exponential pre-computation time, that this still ought to be a hard problem. Assuming that there are one-way functions that are hard to invert even in the presence of advice, which I think most of us think.
So if the person who wanted the answer were themselves an artificial intelligence,
you
could turn them off while you do the quantum computation, and then turn them on and give them the answer immediately in their frame.
No, okay, that's true. You can always do this, right? You can always put yourself into you can always put yourself into deep freeze while your computer is running, right? Then you might worry about but then to keep yourself cooled down with the liquid nitrogen, you need an exponential amount of energy, right? Yeah. Right, and also that this wouldn't note that this wouldn't help for the decoding the Hawking radiation, I don't think, because you would also have to deep freeze the black hole then, right? So yeah.
This has been proposed, yeah.
Oh, all right. I'm sorry, I take it back. Oh, yeah, Mark. Oh, sorry.
A slightly more technical question.
All right.
At the beginning, we had a big discussion about your locality and by 2-bit assumption of the gates. To what extent can that be relaxed? Suppose I had gates that acted on root n bits.
Okay, well the issue is that if you're allowed an arbitrary gate acting on root n bits, then you can just smuggle an extremely hard problem into that. Right? Like take an NP-complete problem, which is defined on root n bits of your input, and then just create a gate that just immediately solves it. Right? And just suppose you have that. Right? So the short answer is, right, if someone gives me an arbitrary unitary operation acting on root n qubits, then I need to, at least, like an engineer would need to know, okay, how do I actually make this thing? In order to make it, they would have to know how to decompose it as a product of smaller operations. Right now, it doesn't matter if our local operations are acting on 2 qubits or 3 qubits or any other constant number of qubits. Okay, that doesn't matter. But as soon as it's a non-constant number, a number growing with n, then we could sort of smuggle in some hard problems. We need to know how to decompose the thing. Yeah. Okay. All right. Yeah.